Emily's was kind of interesting here. She had one of these that was kind of like Cody's, where it was just a line, right? It's actually the generic form of a line. I think somebody had Hector. Oh, we need to talk about that. All right, so let's talk about Hector's here real quick. And so if you have your paper, maybe off to the side, we'll be right there, maybe on a separate sheet, but it's kind of neat to write them right next to each other. So when f of x was 2x plus 3, Hector, what did you have for f prime? 2. He had 2. Now what does that mean? What does f prime is 2? What does that mean? We're recording?
Yes.
Okay. What does it mean f prime is 2? I'll take anybody. Rosa?
That's the slope of the line, or the dot, the point.
Okay. The slope, the formula, this is the formula for the slope, pretty much at any point on this function is 2. Now this is kind of we're starting off with a kind of an interesting one. Does anybody know what 2x plus 3 looks like? What does that function look like?
So it would be like, it would be a line.
Mm-hmm. It's a line. Has y-intercept of 3 and has a slope of 2. Okay? Now, let's think about this logically. At this point right here, what's the slope?
It's going to be...
Nick's saying it silently there. 2. What about this point right here? What's the slope? 2. What about this point right here? What's the slope? 2. In fact, we would say that this has constant slope. The slope is always 2 on that particular line. Would y'all agree with that?
Mm-hmm.
Hector knows that now, but actually went through and did the limit of the difference quotient on this, and he found out algebraically that the derivative is 2. So good job, Hector. You concluded what we also we have verified that graphically. So I think you also did f of x equals negative 4x plus 5. Now, Rosa, you did not do that one, but based on this analysis, what would you guess Hector got?
Negative 4.
Negative 4. Hector, what did you get?
Negative 4.
You got negative 4. Can you all see that?
Mm-hmm.
Because this is a line, and one of the properties of a line is that it always has the same slope. It's the same slope everywhere. So if I said, what's the slope at this point? Well, it's negative 4. What's the slope down here? Well, it's negative 4. The slope, it's always the same steepness. Good job, Hector. Okay. In fact, Emily did for us this whole process in general, right?
Mm-hmm.
She looked at the problem y equals mx plus b, which is really nice because she solved that. She plugged in x plus delta x into mx plus b, and so as a result of that, those b terms canceled. She was able to factor out a delta x. Surprise, surprise. All of you should have been able to factor out delta x at some point. And then the remaining term, either the delta x goes to 0 or there is no delta x. In her case, she got a slope of m. So this is the beginning. I don't know, you should start getting goosebumps. Okay. If I give you a linear function and I say find the derivative, guess what you don't have to do? The limit of the difference quotient. You don't have to do this. You don't have to do what Hector did last night. You just have to say, oh, you're giving me a function, 10x plus 17. The derivative is 10. Ta-da! That's the power of calculus, okay? Is we notice these patterns, okay? Well, actually, we do it the long way with lots of algebra, but then we start to see the patterns, okay? And then we plug it in algebraically, and we come up with what I would call almost like a formula or a shortcut, and boom, we got it. Now you might say, that's great for linear problems there, Mr. Goddard, but what about quadratics and cubics and radical like square root functions, like Nick had, or rational, like Jeremy had. Is there any formulas with that? And well, let's find out. Okay. So Rosa had f of x equals x squared, which kind of like exactly like that, right? And Rosa, what did you get for f prime? I told you had the good answer.
Oh, 2x.
She got 2x. All right. That's interesting. One is not enough to see a pattern here. So the next one that Rosa did was 5x squared. And Rosa, what was that?
10x.
10x.
Oh, you just square.
You're on the right track, but 5 squared would be 25.
Mhm.
But how could you get 10?
5 times 2.
5 times 2?
Yeah.
1 times
Wait,
2
so are you
is
t-
2.
Oh, and so I've been saying, hey, there was a hidden 1 right there. Are you telling me that I could maybe just take this exponent and multiply it by the coefficient?
Ooh.
That would be pretty powerful if that worked. Let's go to Chloe and test that theory. Okay? So f of x for Chloe's was 7x squared plus 2x. Now, Ivan, we're going to test your theory, right? If your theory is correct, now I've actually done two things. I've combined a quadratic and a linear here. But we'll assume that if it works for quadratics and it works for linears, then it works for when they get combined, okay? So Chloe is not going to tell us what her answer was. Ivan is going to make a prediction based on, this is like science right here, right?
Mhm.
He's got a hypothesis, right? We've designed an experiment that will be able to tell us if it's true or not, okay? So Ivan, what would you predict f prime would be in this case? Utilizing your multiply the coefficient by
So
the
it'd
exponent.
be 14x plus 2.
14x plus 2. Chloe, what is on your paper? That's pretty nice. Chloe, you don't have to do the difference quotient anymore when you have quadratics here. Okay? In fact, Cody, we are going to see, Cody had the granddaddy of all quadratics. Oh, it's not here. It's back over. Oh, that was yesterday's stuff. There it is. He had not just a specific number in front of that x. He said it could be any number. It's got ax squared, plus bx, where b could be positive, negative, or 0, plus a c, which we didn't even deal with before, right? And so Cody took care of the most generic, so ax squared plus bx plus c. So if Ivan and Hector's theory here works for Cody's, then it will work for any quadratic we can ever have. Would you all agree with that?
Mhm.
Anything that has blah squared plus blah x plus c, or even if it's just blah squared plus a number, or blah squared plus b, like that. So based on your guys' theory, okay, we're going to see, so f prime, Hector, what do you think that would be using this multiply the exponent by the coefficient trick? What do you think that would be? F prime would be
2a plus b.
2a plus b? Yeah, now here's the catch. We did something else. We didn't just multiply here when we took that 2 times the 1,
Yeah.
okay? But we also took that number right there, that exponent, and dropped it down to like 1. You see how now it's like 1 there? And so 5x squared, we took that 2 and multiplied by the 5. We also multiplied it down, took it down to a 1. You see, sort of like we powered down, kind of like took the power down. So this was 14x1. So here we would have 2a
X.
times x,
1.
and there'd be a 1 right there. I'm not going to write it because we never read it as a 1. So 2ax plus b, and now we say, oh, it wasn't there, it was over here. 2ax plus b. Good job, Cody. We now no longer have to do the difference quotient for anything quadratic. We can just apply this property here, okay? For instance, what if I said f of x is equal to, oh, I don't know, 8x squared plus 3x plus 9. We can apply this property, which I'll list as a formal formula here in a little bit. But we've said you just take that exponent and multiply it by the coefficient. So 16x, drop that power down to a 1, right? What does the 3x turn into? Take that 1, multiply it by the 3, so it becomes 3. And then if you want to think about it, this would be x to the 0, right? I don't know if y'all remember, anything to the 0
Is 1.
so it's really just 1, so we just write 3. And I didn't have anybody do the derivative of a constant function, but the derivative of that 9 turns out to be 0, okay? Which, if you think about it, what if I had a graph that was g of x equals 9? What would that look like?
It would be a line at f of x equals 9.
Yeah, okay, so it's like at 9.
Or g of x equals 9.
G of x equals 9. What's the slope at this point right here?
0.
What's the slope here?
0.
The slope here?
0.
Slope here. Yeah, so the derivative of, so this right here, so if you just do that, g prime is 0. So the derivative of 9 is 0. We're also kind of finding out some interesting things. We find out that it's almost like you can take the derivative of this term plus the derivative of this term plus the derivative of this term. That's called the sum property of derivatives.
Oh, yeah. You read about that.
So we've got that. Let's see, who was next? Stephanie was supposed to do here. They were able to get to a finishing point. Oh, that's okay. I have done all of the hard work on Stephanie's problem. That was x cubed. The derivative of x cubed, if we were to apply this principle, Jeremy, what do you think that would be?
X squared.
3x squared.
3x squared.
Oh, yeah.
So this is called, it's the, you pop down, so you pop this one down, you put it and multiply it down front, and then you power down. Pop down, power down. So bring the 3 out there and then knock it down there from a 3 down to a 2. Okay? It's called the power rule. Pop down, power down. Now some calculus teachers, they, from like on day 2, they say, oh, let me tell you about calculus. It's so easy, all right? Let me show you derivatives. Derivatives are easy, all right? You've got x to the 4th, you take the derivative, boom, take this right here, and it becomes 4, and you take that to a 3, there you go, that's calculus, right? Calculus, got it? You got it? It's real easy, right? It's just moving the numbers, okay? Nobody actually really does that because they love calculus, they love helping you understand it. But it is a rule of teaching of just about anything that you don't teach the shortcut first, okay? Because if you teach the shortcut, this is all you know, right? But think about what we know. We know the algebra. Probably more importantly, we know what this means. We know that this right here is a formula for the slopes of the tangent lines of that function, okay? And we know that this is true based on all these patterns that we've seen here. So f of x equals 1 over x. This is yours, Jeremy, right?
Yeah.
Now, can we rewrite this in a way that looks like one of those?
Yeah. X to the negative.
X to the negative 1. So now let's, think about the way we would apply that. We would pop down, so this would be -1 out front. And then we would power down, so -1 would go to,
Zero.
no.
Oh, no, -2.
It would go to -2.
Okay.
So x to -2. So this would be -1 over x squared.
Oh, okay.
What do you have on your paper there, Jeremy?
-1 over x squared.
That's what he's got.
Wow,
It's true, even for rational functions.
that's so good.
And then, see, Nick, you got the hardest one, didn't you? Alright, if it works for this one, then it works for everything, so. The square root of x. Does anybody know a way that we can rewrite the square root of x as x to some exponent power?
Yes, 1 over x squared, right?
Not quite,
Oh.
no, not 1 over x squared. X,
To,
to the
oh,
1/2
yeah, to the negative
power.
1/2, okay.
no, it's not -1/2.
Oh,
The
yeah.
-1/2 is in the denominator.
Oh, yeah, next to the.
Just to the 1/2
yeah,
power.
the 1/2.
Alright, so let's apply our property here and then we'll see if that's what Nick got. So, our pop down, power down rule, the derivative would be,
It'd be 1 over, it would be 1/2.
1/2, so that's, we're popping down, we're taking the multi, and then times x. Now, when we power down, we subtract 1 from it, so what is 1/2 minus 1? -1/2.
Oh, yeah.
Alright? So, now if you remember, anytime you have a negative exponent, you can actually put it in the denominator. So this is 1 over 2 times x to the 1/2. And then what did we say x to the 1/2?
Square root.
Square root. So 1 over 2 times square root of x. With square roots, you really can't, when you find the derivative, you can't really just take the you can't take the derivative when it's inside the square root. You have to manipulate it into the 1/2 power. Then you can apply the power rule, and then if you want to turn it back into square roots at the end, you can. Now, Nick, what do you have on your paper?
1 over 2.
Look at us. Aren't we awesome? We have collectively discovered what's called the power rule. So if you want to get out your notes, I'm going to tell you the power rule. Well, it's not the power rule for derivatives. It's just called the power rule. Everybody knows the power rule, okay? And that's this. The derivative with respect to x of x to the n is equal to, anybody want to take a shot at it?
Is equal to n x to the n minus 1.
There we go. Good formulaic thinking there, Ivan. Now, if you're not crazy about that notation, I guess you could write it like this. You could say if f of x equals x to the n, then the derivative f prime equals n times x to the n minus 1. That's these two statements over here are the same as this statement over here. This is just an alternate way of writing it. Okay? This is the one-line way. This is the multiple line way. Yeah, that's the power rule. We did see some other rules here too. Actually, we saw the constant multiple rule here. We're almost kind of jumping ahead into next week's lessons, but that's okay. The constant multiple rule was, I'll write it like this, then we'll write it over like that. If f of x equals like some number, like some constant, say c times x to the n, then the derivative was c times n times x to the n minus 1. What I'm getting at is if you have a multiplier out front, okay? Technically, this power rule that I wrote up there only deals when you have, I've limited there to a coefficient of 1. I didn't write it there, but it has a coefficient of 1 that's implied. What we found out was that if you have a multiplier out front there, it really doesn't matter, okay? You just keep that multiplier out front. We also saw something called the sum and difference property, which was that's where, let's say you've got f of x equals, we'll say some function g of x plus or minus h of x. We saw this with the 7x squared plus the 2x. What we could have done is just take the derivative of the 7x squared, you get the 14x, and take the derivative of the 2x, and you get the 2, right? So if you have something that is this plus this plus this plus this, and you're trying to find the derivative of that function, you can literally just take the derivative of this part right here, so g prime of x, and then do plus or minus h prime of x. You take the derivative of this part, and put plus or minus depending on what your situation was, and then the derivative of that part. So we saw that here, saw that with that one. Okay. Lots of different properties that we saw. Tomorrow we're going to look at some different graphs on all of these things. I know I told you yesterday that I would tell you some situations where the derivative doesn't exist, but I'm going to hold off on that till tomorrow. So tomorrow we'll talk about the situations in which the derivative doesn't exist. We'll look at some alternate forms of the derivative, and we'll also look at some graphs, which you're going to love.
What is tomorrow?
Tomorrow is nothing to do. You get a little bit of a break. Isn't that nice? All right. Now you'll have some homework tomorrow, but you don't have to walk in with anything. But we are going to play one last little game. I'm going to give you a card. All I want you to put your name on the card and tell me something that you learned today. 1 or 2 sentences. We got a couple minutes. You can look at your notes. It's not a quiz.
Oh, you want us to write it down?
Yeah, I want you to write it down. We're back out the door.